Good morning, ma'am. Good morning, everyone. Today, I am going to show you the stress strain diagram for ceramic, polymer, metal or alloy, and composite material. For the ceramic material, Figure 1 shows the true stress strain curves of iron and glass. The, the stress strain curve for glass is that blue line. As you can see, it shows a linear behavior that after the maximum tensile strength is applied, crack initiation were detected. This shows that the glass fracture in a brittle manner, and ceramic materials are brittle, so their stress strain curve are usually simpler compared to the stress strain curve of other materials. Figure 2 shows the stress strain diagram for aluminum alloy. Aluminum alloy has considerable ductility despite the absence of yield point, as in structural steel. It is clear in the figure that the initial portion of the stress strain curve is linear with recognizable proportional limit. So as we can see, the stress strain curve for metal or alloy shows different behavior compared to the curve for ceramic materials. It actually has four regions: linear region, region of elasticity, necking region, and the rupture point. Based on a figure, the linear region starts from 0 to about 20 kilopound per square inch. Here, the slope corresponds to the Young's modulus, where the greater the Young's modulus, the stiffer the material. Next is the region of elasticity. From the figure, it starts at around 20 kilopound per square inch. As you can see, it is where the linear behavior of stress strain diagram starts to show a curve behavior. Third is the necking region. It appears when the ultimate strength is achieved. From the figure, it is around 35 kilopound per square inch. And the last is the rupture point. It is where the specimen fractures. Figure 3 shows the stress strain diagram for polyvinyl chloride obtained from tensile and compression test. The curve of PVC is dependent on hydrostatic pressure. This results to the difference between the tensile and compression flow stress of a material. From the graph, the darker curve is the tensile stress and the thinner curve is for the compression stress. For now, let's take a look at the tensile stress of the PVC. From 0 to 50 megapascals, we can see that it shows a linear behavior. This is where the stress is proportional to the strain and deformation is reversible. This shows that the diagram obeyed de Hooke's law. Also, the straight line of the curve gives the elastic modulus of the material, and the maximum stress of the PVC is around 100 megapascal. Figure 4 shows the stress strain diagram for wood titanium oxide composites. It is the red line in the graph. The stress applied here is a compression stress. As you can see, based from the graph, it exhibits a linear elastic region followed by a yield point. Then after that, it continues to deform with steadily decreasing stress. Most composite materials shows two different moduli. And in this figure, we could also see the existence of these moduli in 5.5% strain and 6.2% strain. Most stress strain diagram for composite materials shows this behavior. This indicates that there are multiple instances of failure where the load is reduced abruptly without a full break in sample.